I have given us a graph that looks kind of like this. And we've got 300 over here. I called that 80 and that 50. And this is u. And this is f of u, which is the derivative of u. So this is our du dt graph. And I've said that this graph represents how our population of urracas is changing over time. So my vertical axis here represents the derivative or the change in that population plotted versus the actual population of urracas. So the first question that I've asked is, what are the equilibria for this system? And if I'm looking for equilibria and I haven't been given the equation, I still want to be thinking about equilibrium means where is the derivative equal to 0? Well, on this graph, because the vertical axis is my derivative is equal to 0 at 0, 50, and 300. Now 80 is just kind of on there, not necessarily as a distractor, but 80 is on there representing the peak, but that is not a place where my derivative du dt is equal to 0. So I'm going to list out my equilibria as 0, 50, and 300. Now the next step is we've been asked to determine the stability for each of those equilibria. Are they locally stable, locally unstable? And this, we're going to go back to our graph and think about what the derivative really means. Well, everywhere above this axis, I know that my derivative is positive. So everywhere up here, I'm just going to write it as u prime is greater than 0. And if we think back to what that means from first order calculus, if the derivative is greater than 0, then my function is increasing, which means u gets bigger. That means that in this portion of the curve and in this portion of the curve, because that's where we're above the axis, I know that the values of u should be getting larger, which means my larger u values are to the right. And I'm just going to draw in some arrows for myself, showing that we would be moving to the right. And the opposite is true when we're below the axis. Down here, I know that my u prime is less than 0, or it's negative, which means u gets smaller. So everywhere that the curve appears below the axis, my arrow should be pointed to the left, forcing the population to move in the direction of smaller u values. Well, that's going to let me see right here that my equilibrium of 0, if we move away from 0 just a little bit, we get pushed back towards 0. So we would say that u equals 0 is locally stable. We have another locally stable point over here at 300, because if I move away from the 300, I get pushed back to a value of 300. So u equals 0 is locally stable, as is u equals 300. U equals 50 is unstable, because if I move away from 50 just a little bit, I'll get pushed towards one of the other equilibrium. If I get just a little bit above 50, then I'll get pushed all the way over here to 300. And if I get just a little bit below 50, I'll get pushed down to 0. So u equals 50 is unstable. Next up, if u initially equals 100, sketch a graph of u of t. Now this one's a little bit of a stretch, but we're going to use all of our skills here. If u of 0 is 100, this graph is going to tell us what happens to u. So I'm going to start here, there's 80, so I'm starting here at a u value of 100. And this curve tells us how we're going to change. So if I go to this curve, then we started out at 100, and now we're saying that the change is a positive value. Well, if the change is positive, then I know that I'm going to increase from 100 to something else. And I'm going to keep increasing because my derivative continues to be above the axis here. My curve is above the axis. I know that all of these values are going to represent positive change. So we start at 100 and we head towards 300. So if I were to graph that, thinking about now my horizontal axis being time and my vertical axis being u, we're starting at a value of 100, but over time, I know we're going to approach this asymptotic value of 300 because 300 is our stable equilibrium. So this graph, I'd start at 100 and I would slowly increase over time, heading towards that equilibrium value of 300. Now that's also just told us what the long-term behavior of this function is. With an initial condition of 100 urracas, over time, my population will stabilize at 300. And for that last part here, if U represents the number of urracas per square kilometer in a certain geographic region, what can we say about the equilibrium in biological terms? So this is really just practicing saying words associated with math. And I kind of just did that, but if we start off with an initial population of 100, then it looks like this ecosystem can support only 300 urracas. So we will approach that value, that equilibrium value of 300 after a very long time. So the question in the chat is it only an asymptote if it's a stable equilibrium? Yes. So technically, like if I were to draw out solution curves for lots of different values, for lots of different initial conditions, then I might draw that out looking like here's, if U equals 0, we stay at 0. And if U equals 50, we stay at 50. And if U equals 300, we stay at 300. But when we start to layer in different solution curves for different starting values, because 50 is unstable, nothing will asymptotically approach 50. So if I start anywhere between 0 and 50, we're going to asymptotically be approaching 0, but not approaching 50. And if I start anywhere between 50 and 100, right, we're going to be heading towards, or 50 and 300 will be headed towards 300. So we wouldn't say that 50 is an asymptote because nothing has long-term behavior heading towards 50. First part asks us to draw the matrix diagram that's modeled by this Leslie matrix. Well, I know from looking at this matrix, because it's 3 by 3, that we have 3 age classes. And in this statement of the problem, we've been told that those age classes we are going to call juveniles, subadults, and adults. And if I think about what this Leslie matrix is saying, I know that we're going to take this matrix, multiply it by some population in this order, some distribution of juveniles, subadults, and adults. And the result will be the population distribution of juveniles 1 time step later, subadults 1 time step later, and adults 1 time step later. So if I were going to draw out this picture is going to represent what happens with this matrix multiplication. So to get the new juveniles, meaning that top row of our answer for the matrix multiplication, we'd end up doing 0 times the current juveniles plus 0 times the current subadults plus 0.33 times the number of adults. So the only arrow that I would need to draw on my matrix diagram is from the adults to the juveniles with a coefficient of 0.33. Thinking about my next row and how we get our new subadult population, well, we can think about that from an age class perspective, meaning juveniles grow up to be subadults, but adults can't go back in time. So we're only expecting an arrow from our juveniles to our subadults. And that works itself out with a matrix multiplication. So to get that next row, I'd have 0.3 times my juveniles plus 0 times my current subadults plus 0 times my current adults. So I'll need 1 arrow from our juveniles to our subadults with a coefficient of 0.3. Now I can also think about that as telling me the survival rate. So 30% of our juveniles survive to become subadults. And last, for our adults, there are 2 ways that our adult population that we are going to get the numbers for our adult population next year. We've got our subadults that are going to grow up and our adults that are going to survive 1 more time step. So I'm expecting an arrow from my subadults to the adults and an arrow from my adults feeding back into the adults, assuming that some of them survive another time step. Well, if we look at the matrix multiplication, I'd have 0 times my juveniles. You can't skip being a subadult. 0.7 times my subadults. So there's my coefficient right here. So 71% of my subadults survive to become adults. And then 0.94 times my adults, meaning 94% of the adults survive another time step or another breeding cycle. So there's our matrix diagram. And I suspect I've already answered all the questions in my other parts here. But what percentage of juveniles survive to become subadults? 30%. Are subadults capable of viable offspring? So this one, we can either look at the original matrix or the diagram that we built from it. But if our juvenile are our offspring, and there's no arrow from my subadults into the juveniles, then no, the subadults can't produce offspring. And we can also look at that because it's a Leslie matrix. I can look at the top row, which represents the fundity, or the average number of female offspring produced by each female in a breeding cycle. And this says an average number of 0 offspring from our juveniles, an average number of 0 offspring from our subadults, and an average of 0.33 offspring per female adult. I'm going to get through this last part, and then I see that we've got a question. So if there are initially, so now I'm being given an initial population here, so I'm going to erase this part. If there are initially 310 adults, 100 juveniles, and 30 subadults, how many are in each age class after 1 cycle? So this is really a matrix multiplication problem. So I am looking at 0 times 100 plus 0 times 30 plus 0.33 times 310. I'm not feeling terribly mathy at this moment, so I'm going to pull out a calculator just to make sure that I don't make arithmetic mistakes. So I've got 310 times 0.33, and that is going to give me not a very nice number to think about if these are actually owls. I don't like to think about what 30% of an owl looks like. But remember, these are large averages over time. For my second row, I'm going to have 0.3 times 100 plus 0 times 30 plus 0 times 310. That's going to be 30. And on this bottom row, I'm going to have 0 times 100 plus 0.71 times 30 plus 0.94 times 310. And I'm definitely doing those last two with a calculator. Plus 310 times 0.94. And that's going to give me 312.7. Now I know these numbers are not perfectly matched, but these are actually pretty close to this distribution right here, which I didn't ask us about, but this is hinting that this is probably pretty close to being an eigenvector. It's not exactly an eigenvector because we didn't get exactly the same numbers back out, but I bet it's pretty darn close. So overall, I know that we're looking for some kind of equation that is going to look like, oops, the rate of change for the amount of the drug in the patient is the rate in minus the rate out. And let's just start looking at what's coming in and what's going out. So we know that what's coming in is coming in at 2 milligrams per cc. And I know that it's coming in at a rate of 3 cc's per minute. So now overall, in terms of my units for this piece, I'm looking at 6 milligrams per minute. And that's not changing. That's a constant given in the problem. Now what's coming out, this part's a little bit trickier. So for starters, one thing that we know about what's coming out is that it's coming out at 60 cc's per hour. So already I know I have a unit conversion problem, because over here my time is in minutes and over here my time is in hours. So I'm going to fix that by multiplying by 1 hour per 60 minutes. So now I know that really what's leaving is leaving at a rate of 1 cc per minute. Now the concentration of what's leaving, that's the fun part. Well, the concentration of what's leaving, I know that A is the amount of drug in the patient. So I've got A milligrams of the drug in the patient. The question is, what's the volume? Now there's the fun part. So we said that the volume of the affected systems was 1,000 cc's. But I made this problem extra tricky because I'm adding 3 cc's per minute, but only losing 1 cc per minute. So that means each minute I have a buildup of 2 cc's. Or we started with 1,000, and each minute I need to add 2 more. So if I ditch the units here, I'm going to have A over 1,000 plus 2t. And that is also going to be in milligrams per minute, because this bottom part, that volume, has volume in cubic centimeters, which would cancel out with those. Which means we would be looking at 6 minus A over 1,000 plus 2t. Problem. And here's my patient. We started off with 1,000 cubic centimeters of volume of the affected systems. But the volume of what we're pumping in we're pumping in at 3 cubic centimeters per minute. And the volume of what's leaving is leaving at 1 cubic centimeter per minute. So because that volume is changing, we need a way to represent what the volume is at any given point in time in minutes. So if we were to just chart this, when t equals 0, our total volume was 1,000 cubic centimeters. But after 1 minute, I've had 3 come in and only 1 leave, which means my volume has increased by 2 cubic centimeters. If I go another minute, I've had another 3 come in, but only 1 leave. So now I've added another 2 cubic centimeters. So at any time in the future, I'll just call it time big T. At any time in the future, that volume would look like 1,000 plus 2 times the number of minutes we've had. Good times? So for that term in the differential equation, what's coming out for any of our tank problems, what's coming out should look like whatever letter we've used in the problem, A, X, Q, Y, divided by the volume, because this is our concentration piece. So for that particular case, we had the amount of stuff divided by our volume at any time, which is 1,000 plus 2 times the number of minutes we've been building stuff up. Well, in this problem, I'm asking us to both solve the differential equation explicitly and also estimate a solution using Euler's equation. So let's start with the estimate. And the thing I've asked us to estimate is P of 1. And I've said that we're going to use 2 time steps. So if we're going to use 2 time steps and we have to get from time 0 to time 1, then that must mean that each of our time steps is 0.5. I like to do these with a chart, so I'm going to list this out. We've got our T, we've got our P value, then we're going to calculate our slope. And finally, we're going to put all of that together to get our new P value. And just as a quick refresher, this is coming from our linearization formula, which means our new P value is going to be the P value we were just at plus our slope times some brief time period, how long we've moved in that direction. And when we talk about Euler's equation, we usually call that H. So we're starting at a T of 0 and a P of 2. Well, plugging that into my differential equation, that means that dp dt would be equal to 3 times 0 plus 1, or 1. Which means my new P value, we're starting at 2, and we'll move in the direction of the slope 4.5 of a time step. That's going to give me a value of 2.5. So if I were to pause here, that 2.5 means P of 0.5 is approximately 2.5. We haven't gone far enough. We're trying to get to P of 1. So now I'm standing at 0.5, 2.5. We're going to repeat the process from there. I'm going to calculate my slope. So I've got 3 times 0.5 plus 1. Well, 3 times 0.5 will be 1.5 plus 1 is going to give me 2.5. So to get my new P, I need the P value I'm at right now plus my slope times my time step. My time step for the whole problem, we're not taking different size steps. We're always taking a step of size 0.5. Well, 2.5 times 0.5 is 1.25 plus 2.5 should give me 3.75. And that is approximately P of 1. So that's what we were looking for. We were looking for P of 1 is approximately 3.75. The second part of the question asks us to solve the differential equation explicitly and compare our result to our estimate from the first part. So for the second part, if I'm going to solve this explicitly, well, it better be separable in the context of 17b, which means it's either going to be a pure time differential, autonomous, or neither, but separable. Just to review some vocabulary, I'm going to come over here. Everything on this side, the only variables we have are the variables from the denominator over here, which makes this a pure time differential. Every pure time differential is separable, and every autonomous differential is also separable. So I know this one's separable. That means I'm going to start by multiplying both sides by dt. And when I do that, I'm going to end up with dp is equal to 3t plus 1 times dt. Now we're ready to integrate both sides. When I integrate on the left-hand side, I just get p. When we integrate on the right-hand side, I end up with 3t squared over 2 plus 1 times t plus some constant. Now to solve for the constant, we have been given an initial condition. So I'm going to want to take that t equals 0, p equals 2 initial condition to solve for c. So I'll plug in 2 for p and 0 for t. 0 plus some more 0 is still 0. So I get that c is equal to 2. And if c is equal to 2, that means we can solve our differential equation to say that our level of phosphorus at any time t is equal to 3/2 t squared plus t plus 2. And if I want to compare that to the estimate that we got using Euler's method, this would tell me that P of 1 is exactly 3/2 plus 1 plus 2. So 4.5. Well, they're not that close, but I tried to make a problem that was pretty easy to do without a calculator. Again, and so this question in the chat, as of like 2 minutes before co-class today, no, he has not listed any information about the final in Canvas. Walking up to this thing, we might need to know vocabulary in terms of, is it autonomous, a pure time differential equation, is it separable or not separable? Well, looking at this, that y prime, I could rewrite to say dy dx. Since the only variable that appears on this side of the equation is the x from my denominator, we call this a pure time differential equation, which means it is separable. And my first step for separating it is that I'm going to multiply both sides by dx. Now I'm looking at dy is equal to cosine x times sine x dx, and I'm ready to integrate both sides. The left-hand side is just going to give me a y. And on the right-hand side, you might be staring at that and going, oh, I don't like trig. Too bad, trig's fun. Or trig's not fun, but trig exists in your life and will continue to exist in your life. So embrace the trig. When I look at this, part of me might be thinking, oh, is that some kind of trig identity that I'm supposed to know? But then you should remember that Professor Chaudhuri is really not trying to trick you on any of this. he has really placed a lot of emphasis on basic u substitution. So that's what I'm going to reach for here and ask myself, does the derivative of one part equal the other part? Why, yes, it does, because the derivative of sine is cosine. So I'm going to do a u substitution, and I'm going to come off to the side, and I'm going to let u be equal to sine of x, which means that my derivative is cosine of x dx, which conveniently I have in the problem. So when I rewrite this, I'd be looking at the integral of u du. I'm ready to integrate that. So when I integrate u, I'm going to end up with 1/2 of u squared plus a constant. And then as my final step, because the answer was asked in terms of x's and y's, I want to make sure to turn this back into x's and y's. So this is going to look like 1/2 of sine of x squared plus a constant. And that would be my final answer over there. I think that's going to be enough space to handle this one. So if I look at this in terms of vocabulary, again, I can rewrite that y prime to say dy dx. Because this side of the equation has both x's and y's in it, it is not autonomous. It is not pure time. It is non-autonomous because I've got both x's and y's in there, but it is separable. And my first step to separate would be to multiply both sides by dx. And once I do that, I recognize that on the right-hand side, I still have x's and y's mixed up together. I'm going to need to divide by that y cubed to separate them. So I'll have 1 over y cubed dy is equal to x dx. Now I've got my y's on one side, my x's on the other, and I'm ready to integrate. On the right-hand side, when I integrate x, I'll end up with 1/2 of x squared plus some constant. And on the left-hand side, when I integrate 1 over y cubed, that 1 over y cubed is really y raised to the -3 power. When I add 1 to the exponent, that's going to give me y to the -2 power, and then we'll be dividing by -2. We got choices for where to go from here, but I know that for sure we need to plug in 0 for x and 2 for y to solve for that constant. I'm going to choose to rearrange and get the y by itself first. Maybe. You know what I'm really going to do first? Look at that and say, I don't really like fractions. I'm going to multiply everything by -2. And if I multiply everything by -2, I'd have y to the -2 is equal to -x squared minus 2 times that constant. And I could just call that some new constant. And look at that y to the -2 and write that as 1 over y squared is equal to -x squared plus some constant. And if I rearrange this to get the y squared by itself at least, I can multiply both sides by y squared and divide both sides by this. So I'd end up with y squared is equal to 1 over. And for no reason at all, I'm going to do the mathematician-y thing and switch the order on this so that it looks like a minus x squared. There is really no reason to do that other than it keeps the minus sign neat and tidy. I think I'll maybe, well, then I guess we'll take the square root to get the y by itself. I was just running out of space. I'm on it. So to get the y by itself, that's going to look like y is equal to, and I'm going to do something weird for a second, but I'm going to say y is equal to plus or minus the square root of 1 over a minus x squared. Now, in general, if I take the square root of something, I could end up with the positive version of it or the negative version of it. But when I go back and look at my initial condition, I know that I need the positive version of it because the y value we're looking at initially is a y value of positive 2. Now you probably would have done that correctly on accident, but I'll do it correctly on purpose. Now I'm ready to plug in my numbers and solve for the value of a. So when y is 2, or y is 2 when x is 0. I don't know why I waited this long because now I've got to square both sides, but we'll live. So if I square both sides, I've got 4 is equal to 1 over a, which must mean that a is equal to 1/4. And my final answer here, I'm going to take that a equals 1/4, put it back in, and I'll have y is equal to the square root of 1 over 1/4 minus x squared. Algebra was a little bit messy, but the calculus part, not too bad. And we're asked to do some things, but bottom line, we're asked to find the eigenvalues and eigenvectors and the equations of the eigenlines. So that last thing, the line through the origin in the direction of this eigenvector, that's what Professor Choduri has been calling the eigenline. It's just like the really long way of saying it. So if I'm going to find eigenvalues and eigenvectors, my first step in finding the eigenvalues is to take the determinant of the matrix A minus lambda I and set that equal to 0. I usually construct this A minus lambda I matrix first because we're going to use it for the eigenvalues and use it for the eigenvectors. We're going to get there by taking that matrix A, 0, 0, -2, 1, and subtracting off lambda times the identity matrix. When I combine this together, I'm going to multiply my lambda through, which would make this lambda 0, 0, lambda. And once I do the subtraction, then my A minus lambda I matrix becomes 0 minus lambda, 0, -2, 1 minus lambda. So that's my A minus lambda I matrix. So my first step, we're going to take the determinant of that. And that determinant of A minus lambda I looks like negative lambda times 1 minus lambda minus 0 times -2. Don't work too hard. It's already factored. Don't multiply it out just to factor it again. Because we're subtracting off 0, I know that my eigenvalues are 0 and 1. Well, I was right. This is weird. We don't usually get an eigenvalue of 0, but my particular matrix gave me 1. But it's okay. We're going to treat it like anything else. So my next step here is one at a time. I'm going to choose an eigenvalue and find the associated eigenvector. Well, finding the associated eigenvector means really at its heart, we're trying to solve this equation AX equals lambda X. And we could do that directly. That's not the way that it was presented in class. So I'm just going to stick with the way that it was presented in class, which means we'd subtract the lambda times X over, we'd factor the X out, we'd do some algebra steps. And really what we're trying to solve is this A minus lambda I matrix times some generic eigenvector needs to be equal to 0. And this is the thing this is going to be our starting point for solving for the eigenvectors. So with lambda equal to 0, our A minus lambda I matrix becomes 0, 0, -2, 1. And we're multiplying that by some generic xy vector, and we need to get 0, 0. Now, when I said something weird happens, When I multiply out the left-hand side, I'll have 0 times x plus 0 times y is equal to 0. Well, that's always true. So it just wasn't helpful. For all of the other problems that we have had, where we got distinct eigenvalues, where neither eigenvalue was 0, when we multiplied out the top row and the bottom row, they give us exactly the same equation. In this case, because we've got a weird eigenvalue, this happened. Nothing went wrong, it just isn't helpful. So we have to look at the second row. And the second row tells us negative 2x plus y equals 0. And this right here is the equation of our eigenline. When we rearrange that to say y equals 2x. So that right there is the equation of the line that the question is asking us for. And we can choose any eigenvector by picking a point on this line. So if I call that lambda 1, then maybe I'll choose my eigenvector to be, if I plug in 1 for x, y would equal 2. So that would be my eigenvalue, the eigenvector, and the equation of the eigenline, or the line through the origin in the direction of the eigenvector. And then we would repeat that whole thing at the bottom for lambda equals 1. A vector, we found those eigenvectors and eigenvalues, but I want to compute a raised to the 15th power times the vector three, 3. So one option to compute this is to diagonalize this matrix and use that formula for PDP inverse. And that is the method the textbook goes through. But in class with Professor Chiduri, he showed a second way to do this. And I happen to prefer the second way because it feels more, to me, it feels more natural than like memorizing this big old blob of a formula. So the idea here is that I want to be able to take this vector 3, 3 and write it as a linear combination of these other two eigenvectors. This is a skill that we might need in 17C, which really is the other reason that I prefer to do it this way. But that means I'm looking to write 3, 3 as some constant times the vector 1, negative 2, plus some other constant times the vector 0, 1. Now you might be really good at doing this in your head. I'm going to go ahead and write out what that looks like. It shouldn't be too bad. If I kind of read through the top row, that would say 3 is equal to 1 times A plus 0 times B. And the bottom row would say 3 is equal to negative 2 times A plus 1 times B. Because the numbers worked out so nice, A is equal to 3, and once I know that, it's pretty quick to solve for what B is. So my A is equal to 3, which means that's a negative 6. And if I add negative 6, if I add 6 to both sides, I'll get that B is equal to 9. So now I know that I can write this vector 3, 3 as, put it over here, I've got A to the 15th. And I'm going to write that vector 3, 3 that we're going to multiply by instead as 3 times the vector 1, negative 2 plus 9 times the vector 0, 1. And that's helpful because even though now my starting point isn't exactly one of my eigenvectors, I can write this annoying vector in terms of the eigenvectors and still get to use the shortcut. When I distribute that a to the 15th through, this first part is going to look like 3 times, now I've got a to the 15th times an eigenvector, which means we get to use this shortcut. The eigenvector associated with 1, -2 wasn't, or sorry, the eigenvalue associated with 1, -2 is equal to -1. So I'd have -1 to the 15th times 1, -2 plus 9 times the eigenvalue associated with 0, 1 was a lambda of 1 to the 15th times 0, 1. Not too bad. If I take -1 raised to the 15th power, that should work out to be negative overall. I got to erase something here. Work out to be negative overall. So this first piece, that's a -3, and I could distribute that into the vector. So that would become -3, +6, plus 1 raised to the 15th power is just 1. And when I distribute the 9 in, I'd have 0, 9, which means my final answer would be -3, 15. Find the average value of f on 3 to 7. So this is testing sort of our integration notation or integral notation, as well as average value. When we find the average value of a function, that formula for the average value looks like 1 over b minus a times the integral of the function from a to b. Well, here's a way that I can kind of test your understanding of this formula, but not make you integrate anything gross. Applying this to our function, because we're looking for the average value on 3 to 7, this would look like 1 over 7 minus 3 times the integral from 3 to 7 of f of x dx. I didn't give us what f of x was. I already gave us what the answer to the indefinite integral is. Well, if that's the answer to the indefinite integral, then I know that I can just take this piece of it without the plus a constant and plug in the 3 and the 7. So this would look like evaluating x squared minus 5 from 3 to 7. Or 1/4 times the square root of, let's see, 7 squared, so that's 49 minus 5, so 44. 3 squared is 9, 9 minus 5 is 4. Now I would probably just leave it there on a test, though I suppose we could certainly take the square root of 4. A lot of times when we're doing area problems, it's helpful to have a picture. Even if you are not feeling super comfortable with drawing a picture, you can always just set it up and try to do it without a picture. I've got 2 functions, and I know that I'm going between 0 and 1. So already, if I'm going to find the area, I got my 0, 1. And really, the only thing we're trying to figure out is who's on top, this thing or this thing. You could always just take a guess and go from there and see if your final answer works out to be a positive number. Or you can put a little thought into graphing the functions, or this is not the choice I would make on this particular problem. You could pick a number between 0 and 1 to plug in to see who was on top. My guess is that trying to sketch a quick graph might work out for a lot of you. And if that doesn't feel comfortable at all, my suggestion, just integrate it. Worst that's going to happen is you got the 2 functions backwards. Don't get paralyzed on the test, not being able to move forward. Make a choice, get some partial credit. So I'm gonna just plug in 0 to get kind of an idea. And if I plug in 0, this over here would look like e to the 0 plus 1. So that's 2. If I plug in 0 over here, that's a y value of 1. It's a pretty good, sorry, I don't even know what I just said. When I plug in 0, that's a y value of 0. So it's a pretty good guess that this thing is probably bigger than this thing. I'm going to roll with it. E to the negative x plus 1 minus x. And that we're integrating with respect to x. Right? Integrate e to the negative x. This is going back to beginning of the quarter stuff. If I have the integral of e to the ax dx, we get 1 over a e to the ax plus a constant. In this case, my a, or the constant that's up there in the exponent, is -1, which means when I integrate this, I would get 1 over -1 e to the negative x. The integral of 1 with respect to x is x, and the integral of x with respect to x is 1/2 x squared. I don't need a plus c because this is a definite integral and I have bounds. We're going from 0 to 1. So I'm going to plug in 1 everywhere. 1 over -1 is just a negative, so I'm going to write that as negative e to the -1 plus a 1 minus a 1/2. And then when we plug in 0, I'd have negative e to the 0, so -1 plus 0 minus 0. So putting that all together, I've got negative e to the -1 plus 1 minus a 1/2. So now I'm at positive 1/2. Minus a minus is going to be adding another 1. So positive 1/2 plus a 1, so that's plus 1.5. If we did this correctly and we got the order on these correct, this should work out to be a positive number, which it is, because e to the -1 is really like saying 1 over e. E is somewhere between 2 and 3. Either way, -1 over e is definitely less than 1.5, and we're done. So we're taking this region and revolving around the x-axis. So in terms of a formula for the volume, I know that's going to look like pi times, I'll just call it like my big radius squared dx minus pi times my little radius squared dx. So a couple things we have to do. We need to figure out the limits of integration, and we need to figure out our big and little radius. I'm going to start with the radii first. I always measure a radius from what I'm rotating around, that axis of rotation, until I hit the function. So my small radius, I hit right there. And it's a constant value of y equals 1. So that small radius is just a 1 that I would be squaring. For my larger radius, I'm going to start at the axis of rotation, and I'm going to get to this outside function, which was 5 minus x squared. So that big radius piece is going to be the 5 minus x squared, whole thing squared. Now, there's a question in the chat about whether you need to worry about washer method for the final exam, and I'm going to go back to, I have no idea because we haven't seen the list of things that are on the final yet. So I'm erring on the side of caution and saying, I'm just going to run through all the things that we've talked about this quarter. And if some of them are not on the final exam, cool, you have less to study next week. So if I keep going here, and by the way, if all I did was take that away, then this wouldn't be a washer problem anymore. And the rest of it, we would still have to figure out in a very similar way. But let's keep going on this problem. So I do need to find those limits of integration. And those limits of integration are going to come from where my two functions intersect. And to find the intersection points, I'm going to set them equal to each other. So I've got 5 minus x squared is equal to 1. And if I subtract the 1 over, I've got 4 minus x squared is equal to 1. And that happens to factor nicely for me. So I know that my limits of integration go from -2 to +2. That was problem 10 from my practice sheet here. Is to find the distance between 2 points. I know it's really kind of a boring problem, but it is one of the skills that came up and was hidden inside of other questions also. So our distance formula here looks like I'm going to take the distance between the two x values, square that, the distance between my two y values, square that, and the distance between my two z values, and square that. Now, in terms of like me doing problems, I'm going to quit there. So we do have a formula for diagonalizing this matrix, finding the eigenvalues and the eigenvectors, but my instructions are to just multiply it out because I promise it's not that bad. So let's start with a squared, which would be take this matrix and multiply it by itself. It's a 2 by 2 times a 2 by 2, so I know that I can do the multiplication. And to get my result, this component is in row 1, column 1, which means I take row 1 times column 1. So I'd have 2 times 2 plus 0 times 0. Right here, this element is in row 1, column 2. So I'd take row 1 times column 2. 2 times 0 plus 0 times -3. This element is in row 2, column 1. So I need row 2 times column 1, 0 times 2 plus -3 times 0. Last, row 2, column 2, 0 times 0 plus -3 times -3, which would give me 9. Well, a cubed says I take that thing and I multiply it by this matrix again. 2, 0, 0, -3 times 4, 0, 0, 9. I'm going to do this one faster. 2 times 4 is 8 plus 0. 2 times 0 plus 0 times 9. 0 times 4 plus 0 times -3. 0 times 0 plus -3 times 9. Well, -3 times 9 is -27. You may have noticed that the magic of this matrix is we're preserving zeros here, and these numbers are really just multiplying by themselves over and over again, which means this a to the 4th would end up being 2 to the 4th, 0, 0, -3 to the 4th, or 16, 0, 0, 81. Now we did some work with finding the actual inverse of a matrix, but we will only be asked to find the inverse of a 2 by 2 matrix in the context of 17b. So here, we're not being asked to take this matrix and find its inverse. We're being asked to show that this is the inverse, which means we're really being asked to verify this relationship, that if I take B times B inverse, we expect to get the identity matrix back. And the identity matrix for a 3 by 3 means we are hoping that we get this matrix that has ones on the diagonal and zeros everywhere else. Which means we're about to do a whole bunch of matrix multiplication to show that this thing is true. Oh, I guess I could have left that there. 1, 1, 1, 0, 0, 0, 0, 0, all the zeros. Okay, so if we go to do the matrix multiplication here, this is a 3 by 3 times another 3 by 3. The insides match. The outsides tell me that my final result should be a 3 by 3 matrix. So I'm going to give us a nice big 3 by 3 matrix to work with. And we're going to have these 9 things to compute, and we would need all of them to match up in order for it to be verified that it is the inverse. So this piece right here is in row 1, column 1. So I'll take row 1 times column 1. That's a 0. That's a -2. And 2 times 3/2 is going to give me a +3. So I've got 0 minus 2 plus 3. That is 1. 1 down, 8 to go. This right here, we're hoping for a 0. This is in row 1, column 2. So I'm taking row 1 times column 2. 0, +4 plus a -4. So far, so good. This is in row 1, column 3. Row 1, column 3. I've got 0, -1, and 2 times 1/2 gives me +1. That is 0. We can keep going. Right here, I'm looking at row 2, column 1. Row 2, column 1. -9/2 plus 0. +9/2, bam, we're good to go. You all willing to take my word for it? It should work out if we keep doing the matrix multiplication, but I'm going to call it good. I asked for the value of K to make this not invertible. Well, not invertible is synonymous with singular. So if I'm trying to make this matrix singular, I need the determinant of this matrix to be equal to 0. And if I take the determinant, I'd have 2 times -2 minus -1 times K. Well, 2 times -2 is -4, and that'll be plus a K. So setting that equal to 0 tells me if K is 4, that matrix will be singular or non-invertible. I didn't ask this next part of the question, but let's pretend I did. Let's find the inverse. If K is equal to 3. Well, if K is equal to 3, then our matrix would become 2, -1, 3, -2. And to use the formula for the inverse of a 2 by 2 matrix, I know that I'm looking at 1 over the determinant times, we switch the primary diagonal, so that would be -2, +2, swapping their locations. And on the off diagonal, we take the opposite sign. So this would become a +1, and this would become a -3. Well, our determinant, if we have 3 in there, I'm looking at -4 minus -3. So that should work out to be overall a -1. So I'd have 1 over -1, -2, 1, -3, 2. And if we distribute the -1 in, that's 2, -1, 3, -2. That thing's its own inverse. That's kind of cool. Let's check that and make sure my math didn't go wrong. So if I take that matrix, 2, -1, 3, -2, and multiply it by itself, I think we're going to get the identity matrix, and it's its own inverse. That's really cool. 2 times 2, that's 4, plus -1 times 3, that's a 1. 2 times -1, that's -2, plus a +2, that's a 0. It's working. 3 times 2, that's 6. -2 times 3, that is also 6. Oh, +6, -6, we're good. There's a 0. And on this last one, 3 times -1, so it's -3, plus a +4, that's a 1. Bam, that matrix is its own inverse. I made it up on accident. Isn't that cool? And then I did ask for u plus v. So let's just compute it really quickly. So u plus v, I have 2 plus 1, and -3 plus 1, -2. So to sketch these 3 vectors, I was going to put them on an axis, but we really don't have to. To sketch these on the same graph, I just need to pick a starting point for u. So this tells me to go 3 to the right, sorry, 2 to the right and down 3. So if I started here, then 2 to the right and down 3, that would be my vector u. Well, v, the vector 1, 1, if I'm going to have to do u plus v, I might as well draw it in to be ready to do u plus v. So v says 1 to the right and up 1. So there is my v vector. And u plus v would be this vector right here. What else did I ask for? I asked for the magnitude of each of the vectors. So let's quickly get our magnitude of u, which would look like the square root of 2 squared plus -3 squared. That's 4 plus 9, so the square root of 13. My magnitude of v would be the square root of 1 squared plus 1 squared, or the square root of 2. And my magnitude of u plus v would be the square root of 3 squared plus -2 squared. So that's the square root of 13. 9 plus 4, yeah, square root of 13. Oh, cool. These two have the same magnitude. That's fun. And then last, I asked to find the angle between v and this new vector u plus v. This is where we're going to use that cosine formula. So I know that generally, if I take some vector a dotted with some vector v, that's going to give me the magnitude of vector a times the magnitude of vector b times cosine of the angle between them. So in this case, we wanted to compute this for v and u plus v. So if I take v and I dot it with u plus v, then I'd have 1 times 3 plus 1 times -1. My magnitude of v is square root of 2, and my magnitude of u plus v is square root of 13, and then I have cosine of the angle between them. So that's that's 3 minus 1. I was kind of already doing the math myself. Thank you. That's a 2. 1 times -2. Thank you. So 3 minus 2, so I'm at 1. If we wanted, we could combine those as the square root of 26 times cosine theta. 1 over the square root of 26 is nothing pretty, so my final answer, I would leave this just as writing theta is equal to cosine inverse of 1 divided by the square root of 26. You wouldn't do anything with that. If it were a web work problem, you could put it into a calculator. In terms of a test, we would just quit right there. And I think I managed to get through all of them.